This article is a sub-article of nuclear power. A nuclear reactor, formerly known as atomic pile, is a device used to initiate and control a sustained nuclear chain reaction. Nuclear reactors are used at nuclear power plants for electricity generation and in propulsion of ships. Heat from nuclear fission is passed to a working fluid, which runs through turbines. These either drive a ship's propellers or turn electrical generators. Nuclear-generated steam in principle can be used for industrial process heat or for district heating. Some reactors are used to produce isotopes for medical and industrial use, or for production of weapons-grade plutonium. Some are run only for research. Today there are about 450 nuclear power reactors that are used to generate electricity in about 30 countries around the world. Mechanism. Just as conventional power stations generate electricity by harnessing the thermal energy released from burning fossil fuels, nuclear reactors convert the energy released by controlled nuclear fission into thermal energy for further conversion to mechanical or electrical forms. Fission. When a large fissile atomic nucleus such as uranium-235 or plutonium-239 absorbs a neutron, it may undergo nuclear fission. The heavy nucleus splits into two or more lighter nuclei, releasing kinetic energy, gamma radiation, and free neutrons. A portion of these neutrons may later be absorbed by other fissile atoms and trigger further fission events, which release more neutrons, and so on. This is known as a nuclear chain reaction. To control such a nuclear chain reaction, neutron poisons and neutron moderators can change the portion of neutrons that will go on to cause more fission. Nuclear reactors generally have automatic and manual systems to shut the fission reaction down if monitoring detects unsafe conditions. Commonly used moderators include regular water, solid graphite and heavy water. Some experimental types of reactor have used beryllium, and hydrocarbons have been suggested as another possibility. Heat generation. The reactor core generates heat in a number of ways. The kinetic energy of fission products is converted to thermal energy when these nuclei collide with nearby atoms. The reactor absorbs some of the gamma rays produced during fission and converts their energy into heat. Heat is produced by the radioactive decay of fission products and materials that have been activated by neutron absorption. This decay heat source will remain for some time even after the reactor is shut down. A kilogram of uranium-235 converted via nuclear processes releases approximately 3 million times more energy than a kilogram of coal burned conventionally. Cooling. A nuclear reactor coolant, usually water but sometimes a gas or a liquid metal or molten salt, is circulated past the reactor core to absorb the heat that it generates. The heat is carried away from the reactor and is then used to generate steam. Most reactor systems employ a cooling system that is physically separated from the water that will be boiled to produce pressurized steam for the turbines. Like the pressurized water reactor. However, in some reactors the water for the steam turbines is boiled directly by the reactor core, for example the boiling water reactor. Reactivity control. The power output of the reactor is adjusted by controlling how many neutrons are able to create more fissions. Control rods that are made of a neutron poison are used to absorb neutrons. Absorbing more neutrons in a control rod means that there are fewer neutrons available to cause fission, so pushing the control rod deeper into the reactor will reduce its power output, and extracting the control rod will increase it. At the first level of control in all nuclear reactors, a process of delayed neutron emission by a number of neutron-rich fission isotopes is an important physical process. These delayed neutrons account for about 0.65% of the total neutrons produced in fission, with the remainder released immediately upon fission. The fission products which produce delayed neutrons have half-lives for their decay by neutron emission that range from milliseconds to as long as several minutes. and so considerable time is required to determine exactly when a reactor reaches the critical point, keeping the reactor in the zone of chain reactivity where delayed neutrons are necessary to achieve a critical mass state allows mechanical devices, or human operators to control a chain reaction in real time. Otherwise, the time between achievement of criticality and nuclear meltdown as a result of an exponential power surge from the normal nuclear chain reaction would be too short to allow for intervention. This last stage, where delayed neutrons are no longer required to maintain criticality, is known as the prompt critical point. There is a scale for describing criticality in numerical form. In some reactors, the coolant also acts as a neutron moderator. A moderator increases the power of the reactor by causing the fast neutrons that are released from fission to lose energy and become thermal neutrons. Thermal neutrons are more likely than fast neutrons to cause fission. If the coolant is a moderator, then temperature changes can affect the density of the coolant moderator and therefore change power output. A higher temperature coolant would be less dense, and therefore a less effective moderator. In other reactors, the coolant acts as a poison by absorbing neutrons in the same way that the control rods do. In these reactors, power output can be increased by heating the coolant, which makes it a less dense poison. Nuclear reactors generally have automatic and manual systems to scram the reactor in an emergency shutdown. These systems insert large amounts of poison into the reactor to shut the fission reaction down if unsafe conditions are detected or anticipated. Most types of reactors are sensitive to a process variously known as xenon poisoning, or the iodine pit. The common fission product Xenon 135 produced in the fission process acts as a neutron poison that absorbs neutrons and therefore tends to shut the reactor down. Xenon 135 accumulation can be controlled by keeping power levels high enough to destroy it by neutron absorption as fast as it is produced. Fission also produces iodine 135, which in turn decays to new xenon 135. When the reactor is shut down, iodine 135 continues to decay to xenon 135, making restarting the reactor more difficult for a day or two. As the xenon 135 decays into cesium 135, which is not nearly as poisonous as xenon 135, with a half-life of 9.2 hours. This temporary state is the iodine pit. If the reactor has sufficient extra reactivity capacity, it can be restarted. As the extra xenon 135 is transmuted to xenon 136, which is much less a neutron poison. Within a few hours the reactor experiences a xenon burn-off transient. Control rods must be further inserted to replace the neutron absorption of the lost xenon 135. Failure to properly follow such a procedure was a key step in the Chernobyl disaster. Reactors used in nuclear marine propulsion often cannot be run at continuous power around the clock in the same way that land-based power reactors are normally run, and in addition often need to have a very long core life without refueling. For this reason many designs use highly enriched uranium but incorporate burnable neutron poison in the fuel rods. This allows the reactor to be constructed with an excess of fissionable material, which is nevertheless made relatively safe early in the reactor's fuel burn cycle by the presence of the neutron-absorbing material, which is later replaced by normally produced long-lived neutron poisons which gradually accumulate over the fuel load's operating life. Electrical power generation. The energy released in the fission process generates heat, some of which can be converted into usable energy. A common method of harnessing this thermal energy is to use it to boil water to produce pressurized steam, which will then drive a steam turbine that turns an alternator and generates electricity. Early reactors. The neutron was discovered in 1932, The concept of a nuclear chain reaction brought about by nuclear reactions, mediated by neutrons, was first realized shortly thereafter by Hungarian scientist Leo Szilard in 1933. He filed a patent for his idea of a simple nuclear reactor the following year while working at the Admiralty in London. However, Szilard's idea did not incorporate the idea of nuclear fission as a neutron source, since that process was not yet discovered. Szilard's ideas for nuclear reactors using neutron-mediated nuclear chain reactions in light elements proved unworkable. Inspiration for a new type of reactor using uranium came from the discovery by Lise Meitner, Fritz Strassmann and Otto Hahn in 1938 that bombardment of uranium with neutrons produced a barium residue, which they reasoned was created by the fissioning of the uranium nuclei. Subsequent studies in early 1939 revealed that several neutrons were also released during the fissioning, making available the opportunity for the nuclear chain reaction that Szilard had envisioned 6 years previously. On 2 August 1939, Albert Einstein signed a letter to President Franklin D. Roosevelt suggesting that the discovery of uranium's fission could lead to the development of extremely powerful bombs of a new type, giving impetus to the study of reactors and fission. Szilard and Einstein knew each other well and had worked together years previously. But Einstein had never thought about this possibility for nuclear energy until Szilard reported it to him, at the beginning of his quest to produce the Einstein-Szilard letter to alert the U.S. government. Shortly after, Hitler's Germany invaded Poland in 1939, starting World War II in Europe. The U.S. was not yet officially at war, but in October, when the Einstein-Szilard letter was delivered to him, Roosevelt commented that the purpose of doing the research was to make sure the Nazis don't blow us up. The U.S. nuclear project followed, although with some delay as there remained skepticism and also little action from the small number of officials in the government who were initially charged with moving the project forward. The following year the U.S. government received the Frisch-Peirce Memorandum from the UK, which stated that the amount of uranium needed for a chain reaction was far lower than had previously been thought. The memorandum was a product of the Maud Committee, which was working on the UK atomic bomb project, known as Tuballoys, later to be subsumed within the Manhattan Project. Eventually, the first artificial nuclear reactor, Chicago Pile 1, was constructed at the University of Chicago, by a team led by Enrico Fermi, in late 1942. By this time, the program had been pressured for a year by U.S. entry into the war. The Chicago Pile achieved criticality on 2 December 1942 at 3:25 p.m. The reactor support structure was made of wood, which supported a pile of graphite blocks, embedded in which was natural uranium oxide, pseudospheres or briquettes. Soon after the Chicago Pile, the U.S. military developed a number of nuclear reactors for the Manhattan Project starting in 1943. The primary purpose for the largest reactors was the mass production of plutonium for nuclear weapons. Fermi and Szilard applied for a patent on reactors on 19 December 1944. Its issuance was delayed for 10 years because of wartime secrecy. World's first nuclear power plant is the claim made by signs at the site of the EBRI, which is now a museum near Arco, Idaho. Originally called Chicago Pile 4, it was carried out under the direction of Walter's Infraargon National Laboratory. This experimental LMFBR operated by the U.S. Atomic Energy Commission produced 0.8 kilowatts in a test on 20 December 1951 and 100 kilowatts the following day, having a design output of 200 kilowatts. Besides the military uses of nuclear reactors, there were political reasons to pursue civilian use of atomic energy. U.S. President Dwight Eisenhower made his famous Atoms for Peace speech to the UN General Assembly on 8 December 1953. This diplomacy led to the dissemination of reactor technology to U.S. institutions and worldwide. The first nuclear power plant built for civil purposes was the AM-1 Obninsk nuclear power plant, launched on 27 June 1954 in the Soviet Union. It produced around 5 megawatts. After World War II, the U.S. military sought other uses for nuclear reactor technology. Research by the Army and the Air Force never came to fruition. However, the U.S. Navy succeeded when they steamed the US Nautilus on nuclear power the 17th of January 1955. The first commercial nuclear power station, called a Hall in Sellafield, England, was opened in 1956 with an initial capacity of 50 megawatts. The first portable nuclear reactor, Alco PM2A, used to generate electrical power for Camp Century from 1960. Components. The key components common to most types of nuclear power plants are nuclear fuel, nuclear reactor core, neutron moderator, neutron poison, neutron howitzer, coolant, control rods, reactor vessel, boiler feed water pump, steam generators, steam turbine, electrical generator, condenser, cooling tower, radway system, refueling floor, spent fuel pool, nuclear safety systems, reactor protective system, emergency diesel generators, emergency core cooling systems, standby liquid control system, essential service water system, containment building, control room, emergency operations facility, nuclear training facility.